Okay, I think we are ready to go. Welcome to the session. So the first presentation today will be by Rajesh, a presentation on the Indian deciHz Gravitational-wave mission prepared by Sendhil and Rajesh. So it's all yours. Let's start.
Okay, thank you. First to say that I'm not Sendhil Raja, I'm Rajesh Nayak. So this is an effort to put forward a deciHz gravitational wave detector. The space-borne detector is worked by a lot of people, which we call ourselves as a GWSAT team. And there is no specific name for the mission as of now. So it started with Indigo, that is where the Indian gravitational wave mission altogether started many years back. So first of all, I would like to say that these our investigation are in a very preliminary stages. So we are doing a lot of investigation, but most of them are just happening and going on studies. So with that reference, I will start. And again, I am not expert on any of experimental these things. Sendhil Raja was supposed to give this talk. He is available online. So if you have any question, you could answer too. So let us go ahead. So we start with this interesting news, which we have all seen in the newspaper, that LIGO India has been funded, apparently with the interesting amount of budget. And we were hoping to see this happy news for a long time. And this is like a boosted all the activities, and it is going to act as a stimulant for many more years and to finish this project successfully. But of course, okay, this is a bit slow like me. So, okay. So the now question comes is, what is beyond LIGO India? Would we, once we build it or given time, we'll go ahead with the certain upgradation and that would go on. But there is at some stage, it looks like third generation ground-based detector. It is not really easy to build on Indian soil, especially considering the large population. Though we have we are a large country, our population is also large, and the reasonable kind of a land might be very difficult to get. Our interest mainly lies in the lower frequency. It is well known. I don't want to impress on that. There is a good amount of science to be done below 1 hertz. What Earth doesn't allow you to do, acts like a wall for all that this is. So the space-based deciHz detector is one of the choices for India to go ahead and to contribute in the GW community. As current stage, we are slightly lagging behind with the ground-based detector, but that would be picked up very soon. Now, this probably has been presented by hand. Overall spectrum of GW and various detection techniques. Probably this is an older one. So there is nothing much here. There is a Big Bang observer in the deciHz band, and we have a ground-based detector, LISA, and so on, millisecond pulsar, and then CMB, and so on. So I'll not spend much time. Let's straight away jump into deciHz. This is just to get the perspective of where we are. This is advanced LIGO sensitivity curve. It is like a bird in hand. And then we have a LISA. Hope one day that mission will be successful. So I also consider that to be a bird in hand. So there seems to be a wide gap in between, it's not, there is no gap there. So we have 1 hertz, which deciding frequency between ground-based detector and ground-based detector and not. On the other hand, this is just representative of some signal. One is GW17 0817 binary neutron star, and first detection, that is GW150914, how it spans over the band. And this is really probably monochromatic here, but from here it can sweep down into the ground-based band, and you can have observations, decihertz acting as a early warning system. So there are ground-based detector, advanced ground-based detector could reach till 1 hertz, and then there is a perfect wall there. This is a ETD sensitivity, which is probably would be it will probably do very well to detect many astrophysical sources. And that has taken as a reference, probably this LIGO, advanced LIGO, probably won't be very active at that phase. Probably LIGO India would be there. One need to be seen based on the various time scales of operation. Now we come to decihertz band. There are already many detectors here. Famous one is a DeciGo, which is a very ambitious project, and there are smaller version of them. And we also have a Lunar antenna. So these are many of the attempt to cover this gap so that you can have an early warning system for many of the sources on ground-based detector and more interesting astrophysics. So I'm really not going details into this. I believe these are all understood. So now the question comes, if India want to go ahead with the one of the decihertz concept, what are the choices we have? It is clear that for us, interferometric detectors are the one which is the best bet. And there are 2 possible choices. There is a LISA-like heterodyne system where you have multiple lasers exchanged and combined using a time delay interferometry. Or you could have a DeciGo, LIGO like Fabry-Fero interferometers, which is fairly complex. I am not sure anybody has successfully done it on the space, keeping all the practical aspects into mind and also our technological capabilities. It was decided that we would go for a simple Michelson interferometer. We just take this thing and put it in the space, as simple as that. Now the question comes is that what should be the ballpark sensitivity? How do we decide? We have not decided to go with any of these sensitivity. I go one slide back and tell a few words about Tiango, which is a Caltech and Chinese collaboration. The Rana Adhikari is a part of it, and because he has a considerable influence over Indian gravitational wave community. And as this Tiango, I could not plot it because there is no data points. There are figures, but I cannot convert them into data point. So what this design is a Michelson interferometer with a few complications built into it. So overall, Indian communities also decided to go with the system, which is a simple Michelson interferometer, and see whether such a interferometer can be conceived or can it give enough sensitivity to go ahead with doing interesting astrophysics. So now idea is how do we go about it? Since we are completely zero on board, there is no exactly don't know how to go. So we decided simply put in few points here and draw a horizontal line, and this line is fixed, you can see that the contribution is coming from the acceleration, proof mass acceleration noise, and it has a specific frequency dependency. It is unlikely that we would be able to completely get rid of this. That would remain. You can see all the detectors have the same slope there. So it is unlikely that we will have such a technology that we can suppress such noise. So that would be the one line. Other one is based on the laser power and length of the interferometer and all that thing. So we decided to go with the three basic configurations, with the understanding that one would be not so good, one we prefer, and the last one is an ambitious one, which you can see as it is going very close to decigo. So with that input, and also how do we decide this preliminary factors, what should be the sensitivity scale? Of course, you could say that IMBH is one of the important source, but probably for the decihertz space-based detector would detect them any scale. So we are ignoring that in design, assuming that any of our design would automatically incorporate the IMBH merger. So one interesting thing which we want to do is an early warning system. That means that we want to see these sources or binaries in the decihertz before it enters into LIGO band. So this is what is being done. We have a colored plot here. We have taken all the LVK detection and put them back into this sensitivity curve and see what is the SNR we get. The first one is not good. This is number 1, 10, and 100. You can see that somewhere in between second and third configuration, we would have a SNR of 1 to 100 and more. So it would be fine if we get the sensitivity curve between S2 and S3, and we would be able to get the many of the sources seen by the LVK would be already coming with a good SNR, and it's possible to have detection. With that idea, we went ahead and selected these three, actually two. The third one is not really a good one. This one is not really. And then these two, and to see whether it is possible to have a Michelson, simple Michelson configuration with few 100-kilometer arm length and would give these kind of sensitivity. So based on the earlier simulation, we have come with the rough numbers. These are rounded numbers. You can see that this would be the factor at which sensitivity would be decided, and a rough band between 0.1 hertz to 30 hertz or a few hertz, so that there is some overlap between the ground-based detector and the space-based detector. So idea is to have a simple Michelson interferometer. These are the work carried out by RRCAT group. So we have Shubhamai here, Sendhil Raja is online, and then Mayank, and all those people have worked on this simple design to see whether how much we can get and what are the kind of configurations we can have. So wavelength is a standard 1064 nanometer. We decided to start with the moderate power, laser power, 10 hertz, 10 watts. So it is, of course, at this stage, it is simulation. We can plug in. So we have been playing around with this 10 to 100 watt, but one should see that this is a nominal number of 10 watt. Mirror mass is expected to be around 10 kg onwards, but probably a couple of tens of kgs. And then mirror diameter is one of the important factor in this case. What happens is when you have a Gaussian beam fixed at one end and there would be a beam divergence, the second mirror would not be able to collect everything. It's a simple Michelson. So you will have a loss, which is a clipping loss because of the finite size of the mirror. So once you take that, we account for everything. We look for mirror size of 0.5, 1, and 1.5 meter. Might look little exorbitant, but currently this is just numbers. It has to be translated into the actual mirror and so on. So some kind of optimization is done for the power coupling is estimated for with the diameter arm length as kept as a free parameter, so that we explore various arm lengths and see which one does a better job with the given power and the given waste length. So one can calculate the shock noise contribution, radiation pressure contribution, and compute the PST for this. This is a simple, we have ignored all other noises such as acceleration noise and many other noise. This is exercise to see whether simple Michelson with the practical or reasonable parameter, we could achieve the given goal to have a sensitivity. So we have run through the various parameters searching. So you have 0.5 mirror with 10 watts, the various arm length, 100 kilometer to 7,500 kilometer. Arm length effect begin to come for the larger arm length, while the smaller arm length, these are much further, that so it looks flat, and these are the various configuration. 1 meter here, 0.5, 100 watt. At this stage, it is just number. Probably will not be able to put in 100 watts. So one has to stick somewhere here on the top row. But we went through several of these exercises to figure out we can go up to 1.5 meters. Some people are confident that in a scale of 10 to 15 years, we should be able to build 1.5 meter mirrors. So doing that, we get all these numbers, sensitivity of 50% power coupling. Okay, this is with the 100 watts, but one can go down here. You can also choose this region where you have a 500 kilometer and 1000 kilometer, and then you get the sensitivity, which is close enough for what we have decided. So, you know, all putting it back into our sensitivity curve. So we have, okay. So these are our toy sensitivity curves, and these are the one which coming from the pure Michelson. So Michelson currently does not account for the proof mass acceleration. It's a simple Michelson. So it would start turning up from here. And then at least in this region, we know that the optical and other Michelson are the dominant noise. So we can hit this floor in between these two curves. And so it is like we can do some reasonable astrophysics, including the early warning system for the various ground-based detector. Of course, at that time, you would have a Einstein telescope, cosmic explorer, whatever, third generation. Then you would have a much closer 1 hertz than current, let's say, 10 hertz or 20 hertz. So this is a basic design at present. So in short, it looked like we can come up with a simple Michelson interferometer to have a interesting astrophysics done in the decihertz band. Of course, going to space is unavoidable, but we have a strong space program, and our space agencies are constantly, we are constantly in dialogue with them. So some of these is not really very surprising. So it looks like we are going in hand to make all these changes and come in. Our investigations are very preliminary. We have to do a lot more on the type of nonsense and budgeting them and get the realistic sensitivity curve incorporating all the noises and then do the simulation of all the detailed studies about the noises. More problems would be coming from such as a proof mass isolation, drag-free environment would be critical technology which is required. Space agencies are aware of these difficulties, which mainly the output has to come from that side, ISRO's side. So we are mostly focusing on the optics and other related details and need to be optimized. Of course, data analysis, India, that is a strong group. It is not really a problem. Can develop tools and include the various sources and things like that. Especially some of this band is overlapping with the lunar gravitational wave antenna. So there could be a lot of overlap and possible to have exchange of ideas and collaboration over the various data analysis tools and methods. Thank you. If you have some questions, I'll be happy.
Thank you, Rajesh. Where are the questions? I guess you have microphones nearby, or do you not? Okay, let's start here.
Yeah, so you mentioned this to be used as an early warning system. So for the ground-based detectors, so the early inspiral part of the signal will be most likely detected by it. And then there are intermediate coalescence of intermediate mass black holes that will completely be observed in this band.
Yes.
So will there be any possibility of overlapping happening between the two different kinds of signals?
No, we have intermediate mass black hole above 500 is only seen in this band, right? So that you are limited. I think LIGO can see up to maybe 200, how much? 500? Archana? 500. So that's possible on that, right? Because IMBs are very bright sources in this case, so we are not really worried about them. On the other hand, you can see that neutron stars or stellar mass black holes, their SNRs can be poor because the getting sensitivity down in the decihertz is a lot harder. So you have this type of thing. So these are the best of the sensitivity. So if you consider the Earth-based detector, their sensitivity are further lower, but their frequency is higher. So we expect the more impact would come in the stellar mass black hole or neutron stars or combination. And early warning means it's really early based on when you start seeing them. It could be anywhere between 5 years to, few weeks. So it's not that we are telling, okay, it's coming. No, you can just really go to detector and improve the sensitivity, and 5 years you can wait.
Yes.
Thank you for the presentation. So there's a question. So what are the benefits of going to space? Because, for example, there is BDESIGO, which is planned to maybe fly on the Earth orbit, and it already can do some valuable science. So I was just curious, on your opinion, what is the benefit of being on Earth orbit versus being in space?
You are asking difference between the heliocentric and geocentric orbit?
Well, not exactly the difference between the orbits, but why would one prefer to use that orbit or that orbit?
Okay. So, yeah, space agencies would like to put it in a geocentric orbit. It is because it's simpler, less expensive, and so on. There are several problems. I see it. We have not exactly decided. I have never told anywhere that what orbits we are telling. That's because we are still seriously weighing out all the factors. So one of the important factor in this case is what you call is the flexing or the differences in arm length. When they're going in Keplerian orbit, it is impossible to keep the arm length exactly same. It can be done only to the first order in ellipticity. That's like LISA orbit, which is done with all this full understanding. Now, the same thing can be done with Earth orbit too, but the problem is when you have a heliocentric orbit, the orbital scale is 1 year, okay? And this is going to be a day or few hours. So your arm length fluctuation happens at the really short time scale, and that would have a significant impact on the laser noise cancellation. We are not going for the system like LISA, where you have a heterodyne system. We are using simple Michelson. So L1 have to be equal to L2 to be very precisely. And that is easily achievable on a heliocentric orbit, because it would be almost few micrometer change in the L1 and L2, but it is significantly larger for Earth. So that's one of the major factors. And there could be other factors such as ions interacting with the laser path, and we are considering all these factors and trying to come up with the yes or no answer for this.
Thank you.
I think there was another question up there. Okay.
Okay. So I'm myself involved in, and I know a number of people are involved in various forecast studies for DECIGO. So I'm wondering, so one source of haziness or confusion is where to put the lower frequency cutoff.
Yeah.
So what would you recommend is a good lower frequency cutoff for DECIGO? Because there was one slide where you said it's 0.1 hertz to 30 hertz. But if I look at that sensitivity curve, it seems to go below 0.1 hertz. So do you have a recommendation for that?
No, I don't have recommendation for deciHz, but I can tell you what did our study indicated. So we started with again 1.5 point, right? There is no, this is our starting point. This 1 point, it is at 0.1 hertz. This number we simply wrote down with hand and say that would be our this thing. Of course, it's not that true. Once we did that, this point can shift here. We did all that study. I did all the this thing. One thing is that it seems to be very marginally affecting many of the science which we are doing. Why it is that what we have looked, one is IMBH. IMBH is like a washout, right? It's going to sweep through this band with very high SNR, and you can see literally everywhere. It just small, these changes does not matter. Other case where it would matter is something which does not follow this binary like power. This is power law which it follows, right? Suppose you have monochromatic source. Actually, Arunava has sent me a plot, but it was too early in the morning to put it in my slide, so I did not put. So there you have some point. That is the only source I see that which requires some amount of fine tuning of this if you want. Binaries really does not matter, it looks like.
Maybe one last question.
At this stage for us, it is simple. We just shift that point, redo the whole calculation, see how much SNR has changed. It looks very small.
Yes, thank you for the talk. I was wondering, so I'm looking at this image of Tiango and their noise budget.
Yeah.
So they are using these beam expansion and the opposite telescopes, and they're using, or they say 10 dB squeezing, and then they get to 2 10 to the minus 22. Yeah, I was wondering, do you use the similar things or not at all?
We have far more preliminary round. We are going step by step. We are want to realize everything in our own way. So that is which is maybe taking some time.
Yeah.
So we are currently working with the simple interferometer. Squeezing is not done. Before going into that, we have to have a input mode cleaner, output mode cleaner. before the squeezing does not come into picture without all that. So those extension we have to do and see how the sensitivity changes, and then only there are experts on the squeezing and so on, but what stage it would come, I am not sure.
So the lines that are drawn in here are 500 and
Yeah, this would go on
1,000 meter.
something like here, which is
No,
based on
the
the
length
arm
of
length.
the, yes, 500 and 1,000.
Yeah.
The, right?
But if you go for
Okay.
5,000 or
That's probably it,
7,000, then it would come somewhere here.
Okay, thanks.
Okay, I think, thank you, Rajesh, again for your presentation.